Bismillahirrahmanirrahim. Assalamu alaikum and welcome back. Up till now in this course, we have been focusing on theoretical concepts that we can use to design and analyze computer networks. But we are going to talk in this session about a preeminently practical problem in which you have created a network and it's operating, and we want to monitor and manage its operational status. That is, we want to manage the network where we expect that we would be knowing what is the current condition of the network. If there is some error condition, ideally we should be able to report that over a network and also manage it by preferably taking some preventive action. If we do not have such a network management based system, then our network would be operating on the feedback that we get from our users, and this would be kind of like firefighting, in which you are always after you have some problem, you're trying to correct that problem. But if we are more proactive, we can, through proper monitoring, detect problems before they occur. On the internet, the protocol used for this is the Simple Network Management Protocol, around which this session is going to revolve. In fact, the Simple Network Management Protocol, also known as SNMP for short, has a whole framework built around it. So the idea is that in a framework in which we're implementing SNMP, we have network management system known as NMS, and we install agents on the devices that we want to manage, and then we can either periodically poll the managed agents if they have some information, or we may just be checking on their current status. We can also use the agents to asynchronously inform the NMS of any error condition. So this is predominantly the two modes in which SNMP works. The first one is in which the NMS or the manager polls the agents to ask what is the current status of the network. The other way is for the agent to initiate communication and send what is known as a trap message to the manager informing that there is some error condition. Imagine you are the network administrator of some company, and your business depends on the availability of your network. You can imagine yourself as a network administrator of a company which does web-based business. So some problem arises in a network which, if immediately reported to the administrator, may just take a few seconds to correct. But if we do not have a system in place in which proper monitoring is done, it may be that because human intervention is required, either some user has to report the error to you, or the administrator has to manually or physically access the device to see that there is some error. You can see that this is going to cause loss to you in business, and also the network operation is going to be affected. So with this motivation, we approach this problem, and we want to manage, in which management means both monitoring the network and also getting informed if there is some error condition, and also taking potentially some decisions on the basis of that, in which you may want to configure the device remotely as well through the same management protocol. So let me now map out the course of this session, what we are going to discuss. The first thing I'm going to talk about is the SNMP framework, of which the SNMP protocol is just one part. So as mentioned earlier, SNMP is the protocol which runs at the application layer between the manager and the agent. This protocol, the application layer protocol, runs on the UDP protocol, and the manager uses this protocol to request for certain objects. So the first thing that we need to understand is that we need to have some way of identifying the object that we want to access information about. So because to avoid multiple interpretations of the same thing, we need a standardization process in which every object that you may want to monitor has a unique ID. And we would see that in the simple network management protocol framework, there is a technique in which you can define the objects that you want to monitor. And for the commonly used objects, already there has been a lot of work in the IETF body, which is the Internet Engineering Task Force. They have done a lot of work on standardizing the common objects that you may want to ask for. But still, there may be other needs of having objects which are specific, maybe just to your device. So we would learn how to create and define specific objects which we would like to monitor for our own network device, which may not be standardized by IETF. So the overall framework actually has SNMP, and along with it we have SMI, which is the structure of management information, using which we define what we are going to monitor. So with this, we have another concept of a management information base, which is a file in which we define both the macro definitions of what we want to monitor, the entire thing, and exactly we specify out what the monitored object is going to be like, what is its type, what it is going to be about. So to standardize, we need to do a lot of things, and we're going to cover that in the first part of today's session. In the second part of this session, I'm going to give you a whirlwind tour of the space of software that uses SNMP and provides solutions. So we have various NMS solutions, and they essentially depend on the simple network management protocol for their working. And I'm going to tell you very briefly and very broadly about the different products that we have, so that you may use them in a practical sense for monitoring the own network that you have created, designed, and you should be, you may be able to use this and benefit your company and monitor and manage your network. So we start with the first part of today's session. So initially, let me just map out what the network management framework is. If you see on the slide here, as mentioned earlier, you have a device, a machine, on which you are running the SNMP manager software, essentially in which you load information about what objects you may want to get from various devices. This information is added in the form of MIBs. So MIB is a common way of understanding the different objects in which you define and identify the object, and you also specify what the type of that object is. So the manager and the agent have to be aligned and on the same wavelength regarding this. So we ensure that the same MIBs have been added to the manager and the agent. In many cases, the MIBs come pre-installed, and that is especially the case for standardized MIBs. We'll be seeing that IETF has done a lot of work on SNMP and on standardizing various MIBs. And we can just have a ready-made solution. We would just start up an SNMP server on the device that we want to monitor, and we can use the manager to send polls and get the information that we want from the agent. So I'm using alternatively SNMP server and the agent, which essentially mean the same thing. On the target device, we're running some software which is monitoring whatever we want to monitor. And when the NMS comes up as a client and wants this information, this agent would act as a server and return this information back. And this SNMP agent can be run on many different devices. It does not have to be a network router. It can be a network switch. It can be any device on which you have the ability to add some software. So you may make your printer monitorable by adding SNMP support. And there are various examples of even software being monitorable by SNMP. You just need to ensure that you have appropriate MIBs for that. But we are going to talk about what a MIB is and what SMI is and even what SNMP is in much more detail. We start with the discussion on management information base, what we've been referring to as MIB. MIB is basically logically just a database in which you have some structure. MIB can also mean two different things. The first thing is it's a macro definition of the name of the object, what the type of that object is, and the relationships in a managed entity. We would understand this more after an example, but MIB also means that once you've defined this placeholder, this macro definition, the values associated with it would also be, we would call that these values are stored in this MIB. So we have some overloading in the word MIB, so you should be aware and this should become clear from the context. So we're going to talk about three things in our SNMP framework. The first thing is the MIB part of it. Okay, so the first thing that we need to do is, and something that is dictated by the IETF standards, specifically about the dictated by the SMI method of structuring management information, is that every object, whatever you want to monitor, needs to have some ID, and only if it has a unique ID would we be able to agree and we can have trouble-free communication. The way IETF has organized this is in the form of a tree, and at the root of the tree you have essentially a node which we would call root, and everything follows from that. So in a tree there are no cycles, you just have the leaf node is some node of which you don't have any children, and the tree basically works that a node may have some children node, and similarly those children nodes may have some children nodes, and we would call in this case that some node has a subtree. So we start from the root component of the tree, and that is known as just a dot. So every OID can be represented by a number in which you have multiple hierarchies or multiple levels. The first level is the root level. And then historically, because the internet has developed in this way, and at the early phase we wanted SNMP capable for not monitoring not only internet networks or networks that are based on TCP/IP. So for that consideration, the overall hierarchy that you see may sound a little confusing to you now, but you should look this in the context of how the internet came about. So one thing we have is at the start we have the root, and then in the important line of this hierarchy which we are going to follow for the internet, we have ISO at the second level, and beyond that we have ORG, which is a short form of organization, and beyond that we have DOD, which is the Department of Defense of the US, and after that we have internet. Practically all of our concerns would be in this path of the overall tree. The other parts, like I've mentioned, are there for historical reasons, but if we want to monitor TCP/IP based networks, we would be following this path basically. And I've told you the names for these nodes. These nodes can also be called by or identified by their numbers. So the root node is just a dot which would precede all the identification that you make, and the first one refers to ISO, and then you would have a dot and then 3 which refers to ORG, then you would have a dot and you would have 6 which refers to DOD, and then you would have 1 which refers to internet. So essentially all our OIDs would start with 1.3.6.1 because that is what we are interested in given what kinds of networks we have currently. After internet, you have again at the next hierarchy the two things that we are interested in The first thing is the MGMT node, which is basically all the MIBs that have been standardized by the Internet Architecture Board, which is part of the IETF, the Internet Engineering Task Force. In other words, all of the things that we expect to be standardized would come under MGMT. And if you look up this path, this would be 1.3.6.1.2. So everything that is standardized would come under this, but you don't want to standardize everything because there is a lot of bureaucracy in that. And obviously, if you have something that is of interest only to your company, you want to monitor it, but you don't want to standardize it because no one else is doing it. So in this framework, there is a way for doing that as well. And that is through another node at the same hierarchy as MGMT. And this is known as the private node. And after this, you have all the proprietary MIBs. If you recall, MIBs are just definitions of different objects that you want to monitor. And based on that, you can request information from agents using the SNMP protocol. If you want to monitor proprietary devices, chances are, if you want to monitor it, you would need to use a MIB under the private node. So, having talked about the standardized MIBs, our main focus would be on these standardized MIBs. And the one MIB on which we are going to focus on most is now known as MIB2. At the start of the standardization phase, this was known as MIB1, but then it was enhanced. And now what we know as MIB2 is perhaps the most implemented MIB. In fact, it is a full internet standard, which means that if you want to implement SNMP, you have to implement this MIB. What this means is that you would find practically automatic support for this MIB. Every device that implements SNMP would automatically be implementing this, whatever component of this MIB is relevant to them. Let me show you MIB2, and this is defined by RFC 1213. So let me remind you about the process of RFCs. So the Internet Engineering Task Force works on the basis of these RFCs, and they have different levels. Once you propose some standard, and you also have different tracks, but if you are proposing something to be a standard, initially this becomes a proposed standard. And then when things mature and you have a lot of interest in this and you have implementations, then this can move to the state of a draft standard. So this is the second state. The first one is a proposed standard. The second one is the draft standard. And beyond that, the complete form of a standard is known as a full internet standard. And MIB2 is a full internet standard, which means it's the most mature MIB, one of the most mature MIB there is. There is one other MIB, the Ethernet MIB, which is also a full internet standard. But MIB2 is perhaps the most important MIB that you would come across. If you see the structure of MIB2, this MIB2 node has a hierarchy above it, and that hierarchy can be represented as 1.3.6.1.2.1. So let us retrace this. We've already mentioned that iso.org.dod.internet is referred to as 1.3.6.1. The 2 after that is due to MGMT, and after that 1 refers to the MIB2 hierarchy. And beyond this, you have various definitions. The MIB2 subcomponents or the subtree defined by RFC 1213 is the full internet standard. You would also find some other subtrees of MIB2. In fact, MIB2 has many subtrees. Some part of it is not a full internet standard, but the part of it which you can see on the slide now has to be implemented by everyone because this is part of RFC 1213, which is the full internet standard. You see that there are various nodes beneath MIB2, and all of those nodes have further definitions. So sys node under MIB2 has a complete MIB which deals with system-based information. And then obviously inside this MIB, you need to define the objects, and you need to define what type those objects may be. So for example, one object may be an integer type. Another object may be a counter in which you have continuously increasing values, but you may reset the value once it reaches upper threshold. You may also have another data type, which is a gauge data type, in which you increase, but once you reach an upper threshold or a lower threshold, there is no concept of rolling over. You still remain there until there is reset. So this basically tells us that inside every MIB, we also need to define the various objects and their relationships. And we're going to talk about that when we talk about SMI. Other than the system MIB, which is under the MIB2 MIB, you have various other MIBs, and also every one of these nodes is also numbered. And I hope you get the idea now how we can refer to any point now by a number. Alternatively, as we refer to an object by a number, we can also refer to it by the longer name. Something like iso.org.dod.internet.mgmt.mib2.sys. So this is a name-based description of the hierarchy, and you can also do the same via just numbers, a hierarchy of numbers. You also have other nodes at the same hierarchy as system. You have, for example, interface-based objects. You have address table-based objects, which by the way has been deprecated now. Where deprecated means that we are still supporting it, but we expect that this will be phased out in the future. You also have IP-based objects. You have ICMP-based objects. You have TCP-based objects, UDP-based objects, EGP-based objects, transmission-based objects, and also you have SNMP-based objects. And those are all organized neatly in a hierarchy below MIB2. And it is mandatory to implement this if you are implementing one of these protocols. If you are, for example, implementing EGP, then it's mandatory for you to implement this in your SNMP implementation. At this hierarchy, if we zoom in, for example, if we zoom in into UDP, UDP itself is 1.3.6.1.2.1.7. And after this or beneath this, we have other levels of objects. And these are defined if we look inside a MIB. Careful observation would lead us to what the objects mean and how they are defined. And we would require some concepts about SMI and how MIBs are defined, which would come soon enough in this session. So let's move ahead, and after making the observation that MIB2 is an internet standard RFC, let's move ahead, and I'm going to talk about one particular downstream node of MIB2, which is the system group. So system group has many objects, and now I'll show you the various objects, their identifiers, the name of that object, in which I'm omitting the earlier part of the hierarchy. I'm just telling you the last part. And one important thing I'm telling you is the type of that object. And then you have a description which is straight from RFC 1213. You would see that, for example, regarding the system, we may want to know about system description. This is especially important if we are not only managing just a single router, but we are managing thousands of routers, and this is easily the case in a large ISP. Then you may want to know the location of that device. You may need to know the name of that device. You may need to know the contact information regarding that device. If you want to contact someone, who you should contact. And for each one of these information, these have already been standardized as objects. And the reason is that in IETF, we have a lot of stakeholders. Many companies take active part in the discussions. which is done mainly through mailing lists, and they have meetings, semi-annual or even 3 times a year they meet as well, and then they make decisions of how the RFC, how its status is going to change. But they have decided on what are the important aspects of a system that we may want to monitor. And they have come up with what is the MIB2 system group. Because in the RFC 1213, every object that they have come up with, they imagine that to be essential. Therefore, it is mandatory to implement all the objects. So you may see the description from the screen now. Another important point which I've alluded to earlier is the type of the object. And we can see various types. The octet string, we have an object identifier which is just an OID. The number separated by dots representing the hierarchy of the group that you are interested or the object that you are interested in the overall namespace. Let us now have a look at all the data types that are supported in the SNMP framework. And this is, by the way, defined by SMI, the structure of management information, which is another component of the SNMP framework, which we will cover shortly. So you would see that there are various types. Some of the types are in all caps. So for example, integer is in all caps, which basically means that all of the letters are capital letters. Similarly, octet string is all caps, object identifier is all caps, and these are all caps because they have been directly borrowed from what is known as ASN.1, Abstract Syntax Notation.1, which is basically a presentation standard. So the SMI, what we're going to talk about, is essentially a language for defining objects. And it also identifies the type of the object. And SMI basically is both superset of ASN.1 and a subset, because it takes something from ASN.1 and then it adds many other things. So the all caps types are from ASN.1. So the important types that you would see would be the integer type, which is also integer 32. So this can take both a negative value and a positive value. You may also have only non-negative integers in which you only have positive values, and they can come in the form of a counted type or a gauge type. And I've already stated it, but I'll repeat. Counter is when you would keep on counting, but once you reach the ceiling or the threshold, you would start again. So you would reset the value and you would start counting from 0. But in a gauge, our interest is not in resetting, but in if we reach the threshold, we should remain there. Typically, SNMP provides us aggregated counter-based values. And then, for example, if I am asking a device for the number of bytes it has received on a particular interface, typically how SNMP works is that we would periodically ask the device. We would ask, let's say now, and then we would again poll after 5 minutes, and we would take a difference between the counter values to find out how much data has been received. So at the end of this lecture, I would tell you that, in network management, this is considered a relatively coarse-grained method of measurement, where coarse-grained tells us that the measurement is aggregated. You have no way of getting, finer details regarding maybe, for example, you don't know during this 5 minute or between the time you last polled when particularly those packets arrived. And also there are many things in which SNMP does not give us that information, but SNMP has a lot of utility as well. So coming back to the types, you would see that we've talked of integer, we've talked of counter, we've talked of gauge. You also have time ticks in which you are counting in hundreds of seconds from some previous event. And you would keep on doing this, and then after you reach some level, you would again start from scratch. And if you have a string which does not fit in the tight regulations of these types, you can use the opaque type. Okay, so let me give you an example of these data types. We would look inside a Mabh and we would see the various data types that have been defined. Let us have a look at the interfaces group, and you should be able to see on your screen now a screenshot of the various values for objects in this interfaces group, which is part of Mabh2. You would see that interfaces has many objects defined, and some of them are integer types, like the first object that you see is if number.0, and it is of type integer, and it basically tells us how many interfaces we have on this device. And if you look a few lines below that, you have if description, if DESCR, and you see that the type of this is an octet string, and if we interpret the value of that, we would see that you are actually showing Ethernet 0 there. So the value of if description is Ethernet 0. And if we look near the bottom of the screenshot, you would see if admin status, and it is also an integer, but this is enumerated integer in which the integer has some meaning. So it may be that we use 1 if the interface is administratively down, and we may use 2 if it is up. Or we may use, I'm just giving an example, we may use such kind of mapping for various objects. So I hope I have conveyed how various objects have different data types, and so that you may be able to understand the various values that you're getting from the Mabh that you poll. Okay, up till now we have talked about the Mabh2 Mabh, which is the most famous Mabh there is, the most implemented Mabh. But you also have other Mabhs. If you're interested in monitoring more fine-grained details of your host level resources, things like CPU, memory, and so on, you can actually use the host resources Mabh, which is also defined by IETF in an RFC. Initially it was defined in RFC 1514, and then it was obsoleted by RFC 2790, and the host resources Mabh, which is RFC 2790, currently only has draft status, which actually tells us that implementing this is not mandatory. And in fact, many vendors modify this basic host resources Mabh according to their need, and have it as a separate Mabh. But the idea is, if you want some generic information that is more finer detail than the ones that are offered by Mabh2, you may explore host resources Mabh. And you can see the overall name of this group, and this is .iso.org.internet.mgmt.mabh-2.host. So you would see that this host is actually coming below Mabh2, but it is not a part of Mabh2 as defined by RFC 1213. So it's not mandatory to implement. In fact, this RFC has only a draft status, which is telling us that it is implemented fairly widely, but not that it is mandatory. Both Mabh2 and the host resources Mabh actually are polling information about the equipment. But in many cases, we may want to monitor a network as a whole. And that is where RMON Mabh comes in. So this remote monitoring Mabh is actually motivated by the fact that sometimes we want to monitor the overall characteristics of a local area network. And if you see the slide now, you would see that the RMON probe, which is just a device on which this aggregation of statistics from the local area network is being collected, this thing is called RMON probe, or also RMON agent, and this can be polled through SNMP, and NMS can come to this RMON probe and poll information about the overall network. So this is one step ahead from what we have been discussing up till now, where we have been only focusing on monitoring equipment and various interfaces of that equipment. But now we have progressed one step ahead and we are talking of the whole network. And this is an advancement in the overall paradigm of SNMP. The relevant RFC for this is 1757, and this again only has a draft status, which means if you are implementing SNMP, it is not mandatory to implement this. The overall identification of this MIB is 1.3.6.1.2.1.16. And we would not have time to explore this in much detail, but I would advise interested students and practitioners to look it up because this can offer utility to you in your work. Okay, up till now we have only talked about standardized MIBs. Those MIBs that have been standardized by IETF, and therefore it comes under the MGMT node of the hierarchy. But there are scenarios in which we do not want to have our protocol or our objects that we want to define, we don't want it to be standardized. And so in such scenarios, especially where you have proprietary devices and the concern is not shared by the general public, it is only your concern, then we can actually implement private MIBs. And we've already seen how and where private comes in the overall hierarchy. Beneath private, we have enterprises, and various companies have their names beneath this. And it's not necessary that you need to have a company to get some node here. You can register yourself as an enterprise and make your own MIBs. We are going to have a look at two enterprise MIBs. The first one is from Microsoft, and it is going to get information about things that are Microsoft proprietary. We can also, in a similar vein, access information that is proprietary to Cisco devices, only implemented by them, and therefore even the need to monitor those properties is unique to these devices. So Cisco actually has quite an elaborate structure for their MIBs, and a sample of that is shown on the slide now. Okay, having seen a lot of MIBs, both the standardized MIBs and the enterprise private MIBs, now we come to the question of how are these MIBs defined? What is the language of defining these MIBs? I've already stated in passing that the answer to this question is SMI. But let's have a look at how a MIB file is defined, and then we would talk of SMI. If you see on the screen now, you would see a definition from RFC 1213, which is the MIB2. And in this, you see definite format. In the first part of it, you have some imports in which you are importing certain objects from other places. And then you're defining the hierarchy of your MIB. And soon enough, you would then be defining objects in these particular groups. But my idea here is just to show you that we have a definite way of defining and structuring these MIBs. And this is common to all MIBs. This structure is known as the structure of management information, which is part of the overall SNMP framework. So this SMI component defines the name of the objects, the type of the objects, and also tells us how to encode according to this type information that we have defined. So like we've already seen, every object needs to have an OID. That's a specification from SMI. And if you see the slide now, MIB2 has an object identifier associated with it, which is 1.3.6.1.2.1. Everything that is below MIB2 is going to have this prefix at the start of their OID, and the suffix would be specific to those groups. Okay, the first part of SMI is the naming part. Then you have to encode after having defined the type. And we've already seen the types. So, for example, integer 32, practically the same. We have counter 32, we have gauge 32. In more recent version of SMI, we also have the ability to have larger counters like counter 64. So you have a 64-bit value, and because of that we can count to a larger value. So let's now see how we encode objects according to the type that we've defined. And this is according to the standard TLV method, in which you have initially the type, then the length, and then the value, which is shared with how ASN works. So you would see that initially you have the tag, which is telling you what kind of data we have. And then you have the length of data, and then we interpret the value which is after this in context of what we have seen before. So for example, if we want to define the object type as integer 32, there is a well-defined type for it, and that is held, that is placed in the tag. If you see, we have the value shown here, and that is the tag of integer. The second yellow part of the frame is the length of the value, and this is 4 bytes, which tells us that the value is 32 bits, and then the value is interpreted according to the type we have defined, which is integer. If we want to encode some data as 2-byte long string having the value HI, we would have the tag value display that it is a string. So we would choose the appropriate tag for that, and then because HI is 2-byte long, you have 2 characters, length would be 2 bytes, and then after that you would have the characters. In a similar manner, you can encode all the types that you have. For example, if you want to encode an object ID, the tag would indicate that this is an object ID. The length field would tell how long this object ID is, and then you would have the object ID. Similarly, we can represent an IP address. So a valid data type defined by SMI is an IP address. So if this is IPv4, the length would be 4 bytes, and then you can encode the data in the value placeholder. I hope you understand how SMI lets us use the TLV method for encoding data, and this is a flexible method. Okay, let's move ahead and talk about SNMP Protocol, which is the protocol which the NMS and the agent talk over, and the request of objects or object values is made using the SNMP protocol. This SNMP protocol runs over UDP, essentially because UDP is lightweight. You don't want to create a lot of traffic and a lot of overhead just for monitoring the network. If your network is in poor condition, monitoring the network would make it even worse. So because of that, a choice has been made for UDP as the transport layer protocol, and the NMS or the manager can either poll and ask for values for the OIDs from the agents, or it may also receive a trap from the agent, which is an asynchronous way of telling the manager that some event has taken place at managed entity. So let's now have a look at the SNMP protocol data unit, and inside that we would talk of the various SNMP request types. So SNMP is an application layer protocol. The UDP service essentially delivers the stream of data from the source to the destination, but what is the data that we want to exchange between the manager and the agent? And that is shown on the slide. You can send a request for a particular OID, and that would be a GET request. You can also ask for a GET next request, which would ask the agent to send the next value of the next OID. So if you've asked for some value and you want the value for the next OID, you can simply send GET next request. You can also send a bulk request, but we have to ensure that the bulk request is not very, very large, and in some cases you can have an error. But the idea is that instead of sending request for every object, you can send a bulk request. An important point is that we can also use SNMP for setting parameters. That is, for example, we want to administratively shut down an interface or maybe activate it. We can do it using SNMP, but this is considered not a very good way because of security concerns. But we have this option. The asynchronous transfer mode, in which the SNMP agent sends a trap to the SNMP manager, this has the format of the trap message. Let me show you some commands that you can use using net SNMP package. I'm going to skim over this. Syslocation is an object that is part of the system group. If you want to receive an object from this, you would take the OID, and you can use the SNMP get command, which is offered by the net SNMP package, which works over all Linux and Unix based systems. And if you see the syntax here, there are 3 or 4 different fields. The first thing is the request type, and the last thing is the OID. But between these two, first thing is the name of the device that you want to get to, and this will be resolved by the DNS server to an IP. The public in between is kind of a password. So SNMP has a concept known as a community string, which is that if you want to read or write information into a MIB, you need to provide a community string, and typically this is different for read access and read write access. The default passwords are public for the read access and private for the read write access. And unfortunately, I hope you do not make this mistake, but most network administrators do not change this. And because of that, it is very simple for intruders to get information about your network. Okay, now I'm going to give you, as promised at the start of this session, a whirlwind tour of the various SNMP packages that exist. So this is going to be by necessity brief due to timing concerns. The first package I want to talk about is the MRTG package. MRTG package is a shortened form for multi-routed traffic grapher, and this is a very nice package because it builds nice pretty graphs which are built using the format of PNG and GIF, so it's fairly lightweight, and these are already embedded into web pages. So, and it's actually very easy to implement. You just create configuration, and that is also done through Perl scripts, which is automated. You just define the device that you want to monitor, and you give the community string for that, and then using MRTG and SNMP, the manager would pull information and counter values from the device, and then it would graph it. And using this, we can get very interesting insights into traffic. For example, if you observe that there is a definite diurnal pattern, diurnal actually tells us that there are patterns that are happening over a day and over a week. We would cover this in the next session where we talk of internet measurement, so I'll keep the discussion short here. But you can clearly see what time you're having more traffic and at what time you're having less traffic. But MRTG is limited in that it is not an NMS. It does not cater for error messages. It can only poll for values and then graph it. An upgrade of MRTG written by the same author, Tobias Oettinger, who also wrote MRTG, is RRD tool. This is a more advanced and efficient version of MRTG, in which the graphs are better as well, and also the database that you maintain is more efficient. And there are various tools based on RRD tool, and you can just visit RRD tools site and get a whole listing of those tools, and people are doing very amazing things. For example, the bottom graph, the link of which is given as well, is plotting a graph of the ping latencies, and it is not only graphing the median latency, but it is also showing the variation around the median. So for details, I would advise you to visit this link and see how smoke ping works. There are various other software that are also based on RRD. For example, you can draw an internet weather map using RRD tool. in which you can input a map and you can specify where your links are and where your devices are, and then you can have a pretty graph showing the condition of the link and how much traffic is moving on it. If we want to move ahead from simple graphing, simple in the sense in which you are just getting counters and graphing that, you may also consider Nagios, which is a network management system, though not an enterprise grade NMS in the sense that it cannot cater to a huge number of devices, but it is very useful if you want to do it over a moderately sized network. Nagios is an NMS which is open source, and also it's a free software. So you download it, and after some basic configuration, you can discover your network and also start monitoring them. And using a web interface, you can have a kind of a dashboard in which you can monitor the whole network at just a glance. In the same space as Nagios, you also have OpenNMS, which is a very popular open source free NMS solution, in which, as you can see, we have a dashboard in which the various devices are being monitored. And you can also set up alarms here and also various kinds of notifications. So this is very useful, and this is based on SNMP. So you need to understand SNMP to be able to configure this, but SNMP is relatively simple with reference to the first letter of SNMP, Simple Network Management Protocol. But it would require some effort on your part, and then you can have a very good insight into how the network works. And there are various other tools. I'm going to give just a last name. Cacti is also an NMS software which is based on RRD tool, and it has similar properties to the NMS we have seen before. It can give information about hosts and also the network. So let me conclude this lecture now. SNMP Framework provides us a very efficient method of getting aggregate information about system and network conditions, and it allows us to monitor and manage the network. Also, we've seen that there exists a lot of various softwares that are SNMP based that we can freely use for monitoring and managing a network. And lastly, to motivate the coming sessions, SNMP is not a panacea in the sense that it is not magic. It also has some problems, and one important drawback is that it gives us information that is aggregated, especially since we are polling after 5 minutes or so. In the coming sessions, we're going to see methods that are more efficient in the sense that they can give us finer grained measurements of the network, and which helps us to troubleshoot problems in the way SNMP cannot. But having said that, SNMP also has a space in the overall domain of network management. So till next time, Assalamu alaikum wa rahmatullah.